Okay, so this first section we're going to be talking about is electrons go with the flow. It's going to be very little really though about electrons. It's going to be mostly about the fundamentals of electricity and electronic circuits. So anyway, the electrical term for force that causes electron flow is voltage. Now we've all heard that term before. And another term that I'm sure you've all heard is I was hoping it would have a statement there about amperage. But let's talk about voltage. Voltage is the measure of potential. And we think of voltage in terms of, the power that comes out of, when we plug something into the wall at home, we expect 110 voltage to come out of that source there. But there's another thing that's very important too, and that's the amperage, and that's an indication of the rate of flow of the power coming out. But before we get into amperes, the instrument that we use to measure electric potential or electromotive force is the voltmeter. And they've got a little picture there over to the side of a typical display that you might see on a voltmeter. The correct way to connect a voltmeter to a circuit is in parallel with the circuit. And we're going to show you some diagrams later on that will really present why this is important. You can see here they've got a little diagram off to the right there of a very simple voltmeter, and they're measuring the voltage across a 9-volt battery. And I'll tell you what, everybody...
Hey, excuse me, Joe. Someone has an open mic. It's very hard to hear you. If you can mute everybody.
Can everybody go on mute, please? There we go, much better. Okay, so what we've got there in the lower right is a circuit showing testing the voltage on a 9-volt battery. And the way they've got it connected there, it's probably not the best depiction, but what they're doing is they are testing in parallel with the circuit. And that is how you measure voltage. Now, there are several types of rechargeable batteries, and this is important from a ham radio standpoint because so many of the things that we use in ham radio depend on rechargeable batteries. Portable radios, handhelds, and the like. So types of rechargeable batteries are nickel metal hydride, lithium ion, and lead acid gel cells. And this is exactly a question that you might see on the license test. And just so that you know, the correct answer to this question is all of those choices are correct. These types of batteries are not rechargeable. You can see over to the right, you've got what you might think of as your conventional AA batteries. Those are made of carbon zinc or alkaline. Those types of batteries are not rechargeable. Multiplying the watts per hour consumed by the equipment by the battery power rating to determine the length of time that equipment can be powered from a battery. So in other words, if you have a battery that has a certain amperage hours rating on it, if you take that figure that comes from it and divide the amperage that a certain device needs, you'll get the length of time that it can be powered from a battery. So let's say you have a 10 amp hour battery and you have a device that's going to draw about 2 amp hours. What you would do is divide that 10 by 2, which would give you about 5. You should be able to power that device for about 5 hours. The negative return connection of a mobile transceiver power cable should be connected at the 12-volt battery chassis ground. I know that we're jumping around a little bit on some of the questions here, but as we get into this lesson a little bit further, some of these concepts hopefully will become a bit clearer. But this question here relates to the idea of putting, a radio or a transceiver in your car or something like that. The negative connection of that transceiver power cable should be connected at the 12-volt battery chassis. And that's to ensure that you do have a proper ground and there's not any chance of you having a flaky connection between where the radio is and the battery itself. And here they've got a depiction of that. What you would want to do is go to this source right here. You can see the negative terminal of a battery connected right to the chassis. That is where you would want to connect it. And one of the reasons for that is throughout your car, there are places where they actually put grounding straps to make sure that your entire car can act as a ground, but those are not perfect. Over time, those can get corroded. You won't have as good a connection. So the answer, once again, and you'll see this perhaps in the form of a question, is to do that right here at the negative terminal of the battery. Okay, thank goodness. The name for flow of electrons in an electric circuit is current. That's how we think of electricity flowing through a particular device like a wire or something like that. So the name, once again, for the flow of those electrons in that circuit is current. An ammeter is the instrument used to measure electric current. Now, earlier I talked about voltage, and voltage is potential. One way to think about voltage is imagine you go out to Hoover Dam, if you've ever been out there to see that. I mean, it's hundreds of feet high, and there's a massive amount of water behind the dam. That deep, deep water behind the dam is analogous to voltage. That is the potential. That is that store that stands behind the wall. Now, down at the base of the dam, there is a spillway where the water goes through the electric turbines and goes out into I believe it's the Colorado River. Think of the flow of that water coming out of the bottom as the electric current. That is how fast it's coming out there. And the device that we use to measure electric current is an ammeter. And we had a little depiction of a multimeter earlier on the previous slide. Those same types of devices can also measure amperage or current. And here we go. Electrical current is measured in amperes. Metals are generally good conductors of electricity as they have many free electrons, and that's part of their structure. And that's what differentiates a conductor from an insulator. An insulator won't have that. The more free electrons there are, the better the conductor conducts. Current that alternates between positive and negative directions describes alternating current. And in this particular question, they kind of give that away. Current that alternates is alternating current. Current that doesn't, like in the case of the batteries that we just talked about, that's direct current. An ammeter is connected to a circuit in series to measure current. Now, this depiction, this diagram that they've got over there to the right is a little bit better indication of how these things get measured. Here we have a basic circuit consisting of a 6-volt lantern battery. It comes down here through an on-off switch. It goes, in this particular case, they just have a light bulb. And over here, they've got an ammeter. To measure the voltage across the light bulb, they connect to either side of the light bulb. That is what is known as a parallel connection. Over here, where they measure the ammeter, you can see here that the ammeter is kind of taking place of part of the wire as it flows through here. And that is a series connection. So again, the voltmeter over here is measuring voltage in parallel. The ammeter works in series measuring that. Now, something else that they'll get into a little bit later on, and they show it on this depiction, is you can see that little squiggly line there. That's a symbol for a resistor. We'll talk more about them later on. And by the way, there's the symbol over there for a battery in a schematic circuit or a wiring circuit. And there is a light bulb. Even the light bulb has something that's known as resistance. And we'll talk about that a little bit more when we start talking about Ohm's law. Keep wiring between the power source and the radio with heavy gauge wire and as short as possible to avoid voltage drop when transmitting. If you have a radio, for instance, and you power it with a battery in your car or something, you can get to a point where you're drawing quite a bit of current. As a matter of fact, here in my shack right now, for my radio, I've got a power supply that can put out about 25 amperes. And the reason why you want to keep those connections between that power source and your radio short is even electric wires have a certain amount of resistance. And a lot of current flowing through resistance will create a voltage drop across it. So as a rule of thumb, the shorter you can keep those connections, the less chance that you'll have of losing voltage between your power source and your radio. And Nelson, I apologize. I sort of just kind of got into the flow here. I haven't given you a chance to talk at all. But I'll tell you what, I'm also going to take a very short break here. I'm going to turn off the animations in this slide. I thought I did that before I started. And Nelson, if you would like, I'll let you speak to the next couple of slides.
Okay, sure. Actually, could you continue to share the slides for a second?
I sure will. I'm just turning off the animation. I find that I meant to do that before we started. I find the animation to be more annoying than helpful sometimes.
Okay.
It's fine when you put the slides together, but not so much when you're using somebody else's. Okay, no animation this time. You want to talk to this one, Nelson?
Sure. Yeah, I'm Nelson, KA2C. Good evening. Yeah, so power supplies that most hams will use in the shack are actually based on 12-volt systems. So typically the voltage used is actually a little higher than 12 volts for reasons we won't get into, but it's kind of like the battery in your car, and that's where it comes from. But so typically, if you have a power supply rated for 50 watts output, and the transceiver is rated at 13.8 volts, and you might need about 12 amps. Now, we'll get into it later, but if you know how to calculate the power here that's being drawn, it's the amperage times the voltage, right? So if you multiply these two numbers, you get something a lot bigger than 50 watts. But equipment is not 100% efficient. So what's going on here is you're putting in something much bigger than 50 watts or something over 100 watts, but you might get 30, 40% efficiency out of this radio and put out 50 watts, okay? So we'll talk about a little more about that later with Ohm's law and power calculations. Okay, so to change alternating current into direct current or current that's only flowing one direction, use something called a rectifier. And then the circuit diagram over here, that's that little device that has a arrow and a straight line here. That's a diode, okay? And in this particular circuit, we have what's called a full bridge rectifier. So it takes alternating current and sends the current during one half cycle down the output wire on the top, and in the other half cycle, it sends it from the other side down that wire, and vice versa. And of course, in electrical circuits, you always need two wires. You need a source wire and a return wire. So you see that going into the full bridge rectifier and coming out of it. And this other little diagram over here, that's a transformer to the left, okay? So a transformer, typically you would go from one voltage to another and one current to another. So you might have 110 volts here on the input and 12 volts on the output. And if you need 10 amps on the output, you would only need about 1 amp on the input because the power is conserved across the transformer, okay? But yeah, we'll talk more about this rectifier later in these circuit diagrams. Over here, you see this rectangle is called the load. Now, sometimes a resistor is a load, so, but it could be a light bulb, or it could be, in this case, your transceiver, which is, again, in this case, drawing 12 amps at 13.8 volts, okay? So the diode has an anode and a cathode. And typically, you put a positive sign on the anode side of this. And now electrons are negative, okay? So the electrons flow against the diode, okay? The actual physical electrons flow against the arrow, but the positive voltage flows with the arrow. So this is a little confusing because electrons are physical things, and they have negative charge, and the protons, which are actually positive, don't actually move in the circuit, okay? It's the electrons which move. So they actually flow against the arrow, which is a strange thing, but the positive current flows in the direction of the arrow. So that's why it's drawn that way. But the thing that's actually moving is going the other way, okay, because it's negative. Okay, I think we can go into the next slide, Joe.
Okay. And actually, that slide I had in the middle there, Nelson, was just a blow up of the depiction on the past slide. So we're caught up.
Rectifiers and so forth. Okay. So here you have a depiction of alternating current. This here symbol over here to the far left is a symbol for a source, and when it's drawn with this depiction of a sine wave here, positive and negative part, that's meant to be an AC source. And you have the resistor here or the load. So you can see that you have positive parts and negative parts. Now, you know, for our electrical grid and what we see in power supplies, it's 60 hertz power, right? It's 60 cycles per second. So the positive part here is a half cycle, and that would be a half of 1/60th of a second. Okay, so one full cycle, which includes the positive part and the negative part, would be 1/60th of a second. Okay. Now here in the lower part, we have this AC source, and we have a diode and a resistor. So again, the positive flow is in the direction of the arrow. So you see on the resistor here at the top, you're going to get the positive half cycles. And then on the negative part of the cycle, the current is blocked by this diode, and so there's no current flow at all, no voltage across the resistor in that case. So this is a single diode, and you can make a power supply doing this simple approach with a single diode, but you miss the negative cycles in the power supply in this case. Okay. Now a diode actually has a little bit of voltage drop. Okay, so it's not perfect. You know, in a diagram here, it's drawn as a perfect diode, meaning no voltage drop, and it simply changes the direction. But actual realizable diodes have a little voltage drop. And the most common type of silicon diode has about 0.7 volts. There are some other kinds of diodes. That's in the positive direction when it's turned on, when current is flowing through it. There are other diodes that have smaller voltage drops, but we won't talk about that here. Okay, Joe.
Okay.
Okay, I mentioned this earlier that the parts of the diode, and the important thing to remember is the arrow actually shows the direction of the positive flow, but then the physical device itself is typically drawn with a band across it. So this rectangular here drawing depicts an actual diode, and that's what they physically look like, a little rectangular cylinder typically. And they might be 1/4 of an inch or so long for a typical diode that you would buy, a small signal diode, a low power diode. And a band is put on them to depict the negative side, the cathode, okay? So when you insert it into a circuit, you can use that information to help you put it in the correct direction, because it does matter which direction it goes. Now, the same is not true of a resistor. And here's a actual physical picture of a resistor. And color coding is used on resistors because they come in many, many values and span a huge range of values from fractions of an ohm to millions of ohms. So some of the bands tell you the first couple digits of the value, and then one color at the end tells you the multiplier in tens, and then finally another ring tells you the tolerance. Is it a 5% resistor, a 10% resistor, or a 1% resistor, something like that, okay? Anyway, resistor is a very important part of electrical circuits, and you'll see them used many, many times in electronic circuits to divide voltage, to control current, different uses for a resistor. It's also a very simple device, okay? Okay, Joe, I think next slide.
Okay.
And Joe, we'll throw it back to you here in a little bit, just so I can catch my breath, okay?
Okay, sounds good.
Yeah, let me do this slide yet. Types of current flow that is opposed by resistance. So basically any electrical current it will be opposed by a simple resistor. There are different kinds of resistors, and some of them do behave a little differently, but a basic nominal ideal resistor will oppose direct current, that is the simple output of a battery, let's say, or direct current coming from some other source. It will oppose alternating current. It will also oppose RF current. Now, just bear in mind that RF current is actually alternating current. It's just at a high frequency. It's not 60 cycles per second, it might be a million or 10 million or 100 million cycles per second. It's just a very fast kind of alternating current, okay? So all of these choices are correct because a resistor will pose any kind of electrical current. So the units of resistance are ohms, named after Mr. Ohm, of course. And for example, the volume control in an older radio where you turn the knob, okay? That was actually a variable resistor. I guess some newer equipment still use this, but mostly today you have digital controls for this, of course. But your older radios all used a variable resistor, and it was called a potentiometer. Okay. Ohms are you control the value of the ohms when you adjust a potentiometer, and you're varying the resistance when you do that. A variable resistor is actually physically constructed by taking a resistor that has some significant length to it and then tapping it with a metal finger that actually slides across the resistor. So you vary physically the length of the resistor and hence the resistance. Okay. All right, Joe, turn it back to you.
Okay, thanks, Nelson. Okay, let's talk a little bit about insulators. Now, earlier I mentioned that the two types of materials that we kind of think about in electricity are insulators and conductors. The conductors have lots of free electrons, and those are things like metals, copper, silver, gold. Those are all excellent conductors. Other items, like for instance over here, glass is an excellent insulator. And that's often used to protect either people or equipment from the actual electricity. And you can see here they've got, that looks like one of those glass insulators that they used to have on the tops of power lines to attach the wire to it. But yeah, once again, glass makes a very good electrical insulator. The electrical component that stores energy in a magnetic field is called an inductor. And the important thing about this is the storage of energy in a magnetic field. And the device that does it is also a very common electronic device. And they show a very simple one over to the right. And it's an inductor. And I'll tell you what, guys and gal, it is exactly what it's depicted right there. In its simplest form, an inductor is just a little coil of wire. The electric component is usually composed of a coil of wire. Of a coil of wire is an inductor. And you can see here they're depicting a couple of different ways of making inductors. The one there, once again, you see the coil of wire, and it's got some type of cylindrical core in between it. The core can change the property of the inductor. It doesn't necessarily have to be there, but that is one way of making an inductor. Another way is to have over to the right, you can see those little inductors there are actually variable. They've got like a little hex screw on the top of them where their inductance can be varied somewhat. And the type that are shown there are designed to be put into an electronic circuit. So the ability to store energy in a magnetic field is called inductance. I'm sorry, did you have something there, Nelson?
I was just going to clarify a point on the things to the right. They just look like boxes, so it's kind of hard to understand what's what's going on there. Actually, inside the box is a coil, much like you see in the first picture, and the rod that's going through the middle of it there goes up and down as you turn that screw, which varies the inductance. Okay, so you don't see the physical operation of what's going on there in the picture. But if you take that thing apart, you'll find there's a coil inside.
Mm-hmm. Excellent point. Yep. Okay, thanks, Nelson. Yeah, the basic unit of inductance is called the Henry, again named after a famous physicist, as all of these units of measure are. And so inductance, once again, the unit of measure for that is a Henry. Now we're going to get into something that's a little bit squirrely, so hang on there, everybody. We're going to talk about impedance. Impedance is kind of like resistance, but it's the measure of opposition to AC current flow in a circuit. So it's kind of like resistance, but it's not exactly. It's got a couple of unique characteristics of it, and we'll talk about that. And the reason why I say it is somewhat, it is at least analogous to resistance, is because once again, the basic unit of impedance is the ohm, just like it is for a resistor. The ability to store energy in an electric field is called capacitance. And the basic unit of capacitance is the farad. Now down below you can see different types of capacitors and their uses. Now the one I want to draw your attention to is actually kind of somewhat like the simplest form of a capacitor almost. And this is what you see down here. This is a variable capacitor down here. And you can see what it consists of are metal plates that just have a gap in between them. And those variable ones, and I just happen to have one here if my video is still working. I've got one right here that came to me in the mail today. It's for one of my electronic projects. What it has is in the front of it, you see there's a shaft that comes up that runs through all of those metal plates. If you turn that shaft, the amount of plate in between the two plates will vary. And that's how they adjust the capacitance. And something like this is a very common feature in a radio, especially older style radios. They use these variable capacitors as tuning mechanisms. And again, the basic unit of capacitance is the farad. Capacitors can be made out of all different types of materials, though. They can be made with materials like mica, even paper, electrolytic capacitors, and electrolytic capacitors are more common with things like power supplies and the like, because they can store electricity for, they're usually larger size capacitors and they can store more energy, but there are also ones made of polyester and ceramics. The electrical component that stores energy in an electric field is the capacitor. And once again, you can see here, this is about as simple as a capacitor gets. You get a couple of metal plates, a couple of leads off either side. If you apply power to them, in this particular case, they've got a little bit of dielectric in between them. That dielectric can be something, for instance, like mica. And what you have there in its simplest form pretty much is a capacitor. The type of electrical components that consists of two or more conductive surfaces separated by an insulator is the capacitor. And over here on the right, they even show a capacitor here that is made out of a roll of paper and with metal plates in between. Even something as simple as that can create a capacitor. And this here is the symbol of the capacitor. You'll see this when we talk about schematic diagrams and wiring diagrams a little bit later on. But this is your symbol for the capacitor. The electrical component used to protect other circuit components from current overloads is the fuse. And I think we've all had an opportunity to play with these. This is a common thing in both your house and in your car. This is what a fuse does, is if too much current flows through them, it will literally destroy itself. It'll burn itself out to protect the circuit. And the rating of fuses is measured in amperes. And you can see this one up here is blown, and the one below it looks like it's still good. The component that can be used as an electronic switch or amplifier is the transistor. And that statement there is a little bit of an oversimplification because there are lots of different types of transistors. We will talk about some of the different types, but here are some pictures over here depicting them. But that is absolutely correct. A transistor, in a sense, is just an electronic switch. By virtue of the fact that it can take a small change in current and turn it into a large one, it can be used to, switch a circuit where, like for instance, if you want to use a tiny bit of voltage, say off of a solar cell, to control the power of a battery. A transistor is something that can do that for you. Or if you were to apply alternating current to a circuit, you can also use it as an amplifier for audio or for radio frequencies. The names of the electrodes of a bipolar junction transistor are the emitter, base, and collector. That's something you just kind of commit to memory. This is the simplest form. This is what they call a bipolar junction transistor. And again, the three components on it are the base, the emitter, and the collector. Now on these, you can see they've got two depictions. They have a PNP transistor, and the way that you know that from the diagram, although I wish they made the arrow bigger, is you see the little arrow there is pointing in towards the transistor. An NPN transistor, the arrow points out. And there is an important thing about that, because think of that arrow as the direction of the diodes that Nelson was talking about. In this particular case, the current flows from the collector to the emitter. In this case over here, the current flows from the emitter up to the collector. And it will just depend on the type of application you have as to which type of these you would want to use. The term that describes a transistor's ability to amplify signal is called gain. How much gain does the transistor have? And gain is usually measured in decibels. We're not going to get too much into them. Decibels are a logarithmic measure of the increase in power. And the thing that you really need to know is, again, when they talk about amplifying a signal, the transistor's ability to do that is gain. The transistor is an electronic component that can provide power gain. Well, if you can answer that question there, you can pretty much answer this one here. So there are two questions that you may see on the test that are very closely related to each other. The component made from 3 layers of semiconductor material is, you guessed it, that's the transistor. And this is where, before I was talking about the N-type material and the P-type material, those are the sandwiches, if you will, that are put together to create a transistor. In this particular case, here's the NPN transistor, and once again, on the symbol, the arrow points out, and the PNP style transistor, and in this case, the arrow is pointing into it. And this one here, they've kind of got this depicted upside down from the picture that you saw previously. There's another type of transistor that has a gate, a drain, and a source, and that's called a field effect transistor. And its symbol is over here. This symbol is a little bit different than the other one, but there's a couple of different types of them. One is called a P-channel. In the P-channel one, the arrow is pointing out, and an N-channel one, and once again, that's very similar to what we talked about up here with the materials that make up a transistor. The N-channel one, the arrow is pointing in. The abbreviation for a field effect transistor is called FET, or FET more commonly. So the abbreviation FET stands for field effect transistor. Okay, that was the section Electrons Go with the Flow, and I know that that was a lot. While I transition over to the other slides, does anybody have any questions?